This is a tutorial to develop a discrete probability distribution for the dice rollers example that we performed in class. In this problem, we considered the random variable x, which is the number of hits, which was either a 3, 4, 5, or 6 from 10 dice. So some observations that we took, so maybe just looking at 10 of them, we recorded the first 10 entries, recorded 9, 9, 6, 7, 6, 8, 7, 6, 6, and 8 hits. We can use this to estimate a probability mass function and cumulative distribution function for the dice rollers example. So to do this, we can start building a table where the random variable values go in the top row. These would be anywhere from 6, 7, 8, or 9 observed hits. Our frequency of observations were 1, 2, 3, 4 observations of 6, 1, 2 observations of 7, 1, 2 observations of 8, and 1, 2 observations of 9. So using these observations, we can compute a probability mass function. And remember that a probability mass function is the probability that a random variable x takes on a specific value. So for example, we saw that 4 out of these 10 occurrences, the random variable took on a value of 6. So the corresponding probability mass is 4 out of 10, or 0.4. Similarly, the probability that the random variable x takes on a value 7 is 0.2. Probability it takes on 8 is also 0.2. And the probability it takes on a value of 9 is also 0.2. So using these values, we can express the probability mass function as a conditional equation. So probability that x takes on a value of 6 is 0.4. So the probability mass function value is 0.4 if x equals 6. It's 0.2 if x equals 7. It's 0.2 if x equals 8. And it's also 0.2 if x equals 9. We could plot this, for example, using the random variable values on the x-axis and the probability on the y-axis. Have values for 6, 7, 8, and 9, corresponding to 0.4 for x equals 6, and 0.2 for x equals 7, 8, and 9. And we can also compute the cumulative distribution function, or CDF, by creating the cumulative sum of the probability mass function. So the probability that the random variable x takes on a value less than or equal to 6, for example, is 0.4. The probability it takes on a value of less than or equal to 7, which is either 6 or 7, is 0.4 plus 0.2, or 0.6. The probability it takes on a value less than or equal to 8 is 0.4 plus 0.2 plus 0.2, or 0.8. The probability it takes on a value less than or equal to 9 is 1. So all of our observations fell at 9 or below. So the cumulative distribution function we can also express as a conditional equation. So the equation takes on a value of 0 if x is less than 6, which is our first observation, takes on a value of 0.4 if 6 is less than or equal to x is less than 7, takes on a value of 0.6 if 7 is less than or equal to x less than 8, and it takes on a value of 0.8 if 8 is less than or equal to x less than 9, and it takes on a value of 1 if 9 is less than or equal to x, or x is greater than or equal to 9. And we can plot this cumulative distribution function for f of x versus x. We can look at values 6, 7, 8, and 9. So it's the CDF value is 0 if it's less than 6. So I'll mark it here at 0. Then it jumps up to 0.2, 0.4, 0.6, 0.8, 1. Jumps up to 0.4 if it's between 6 and 7. And it jumps up to 0.6 if it's between 7 and 8. And it jumps up to 0.8 if it's between 8 and 9. And finally, if anything above 9, we have a CDF value of 1. Now we can take this derived PMF and CDF values, for example, and compare it to what we'd expect for this particular problem. So we would expect that the random variable x would follow a binomial distribution with n equals 10 trials, since we have 10 dice, and a probability of success of 2/3, because we have a 2/3 chance of getting a hit from any individual die. So the binomial distribution follows a certain probability mass function. So if you look up on a reference, the binomial distribution has a probability mass function, for example, looking at variable k instead of x. So k is the number of successes. We had called previously x the random variable, but it's essentially the same thing. Probability of achieving k successes is n choose k times probability of success to the k power times 1 minus the probability of success to the n minus k power. So in our particular case, this is 10 choose k times 2/3 to the k power times 1/3 to the 10 minus k power. Now there's a couple of cases that we can investigate right off the bat. So we could evaluate, for example, what's the probability of getting 6 successes or 6 hits out of the 10 rolls. So this, just using this equation, is 10 choose 6 times 2/3 to the 6th power times 1/3 to the 4th power. And if you use a calculator to solve this equation, we get a value of about 0.22. We could do a similar evaluation for the probability of getting 7 successes, which is about 0.26. Probability of 8 successes is 0.20, and the probability of 9 successes is 0.09. Now, one of the challenges of comparing this theoretical distribution to our observed values is that we only made observations for these 4 random variable values, 6, 7, 8, and 9. So if we take these theoretical probability mass values, for example, we note that they don't sum to 1. They sum to about, what is this, 0.68 plus 0.09, so it's about 0.77. That's definitely less than 1. So one thing that we may have to consider if we wanted to truncate this binomial distribution and say, rather than getting values anywhere between 0 and 10, so usually 0 is less than x, less than equal to 10. If we want to change that and say that instead x has to be between 6 and 9, we have to make some adjustments to this theoretical distribution to get all of these values to sum to 1. And essentially what we could do is, rather than just calculating the probability of having 6 successes, we could instead change that to looking at the cumulative distribution function for 6, which is probability of x being less than or equal to 6. So it captures all the cases from 0, 1, 2, 3, 4, 5, and 6. And you could use a statistics library, for example, to calculate this, which ends up being something around 0.44. So that would be a good replacement for this particular value if we wanted to truncate this distribution to only consider x between 0 and 9. Similarly, we have to adjust this parameter, since this one only looks at the probability of 9 successes. We could instead look at the probability of having x be greater than or equal to 9. And the important trick for how to consider this is, since we don't have there's no analog to CDF for a greater than or equal to operator, what we can instead represent this as is the probability of having x equal to 9, and then add in the probability that x is greater than 9. And the important thing to note is that this probability of x greater than 9 is really 1 minus probability that x is less than or equal to 8. And this is the CDF of 8. So to just summarize this, the probability that x is less than or equal to 9 is really equal to the probability that x is equal to 9 plus 1 minus the probability that x is less than or equal to 8, which is the PMF value of 9 plus 1 minus the CDF of 8. So think about this a little bit. This one, if we updated this, this would be about 0.1. So it's a very minor change from 0.09. But if you sum up these values, 0.44, 0.26, 0.20, and 0.1, we do end up with a total probability of a truncated binomial distribution